Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're gonna derive the rate law of a given reaction when we're given a certain mechanism. So let's get into this. Okay, so in this problem, we're told that in the absence of carbon monoxide, the oxidation of NO to NO2 by oxygen appears to follow the mechanism given here. So we have 2NO reacting to give N2O2. That's step one. And then the second step is that the N2O2 that's produced reacts with oxygen to form 2NO2. That's step two. And so we're asked first, A, if step one is slow, what is the expected rate law for this reaction? Okay, well, let's go ahead and do that. First, we should determine what the overall reaction is. So when we do that, we can add these two together and we get, since N2O2 is a intermediate between the first and second step, we're going to cancel those out. So here we have N2O2 as a product. Here it's a reactant, so that's going to cancel out. And we're not going to have that in our overall reaction. But 2NO will make it, plus the oxygen. And then that's going to form 2NO2 for the overall. So for the overall reaction, that's our reaction. And so for step one, we're told let's assume that step one is slow. And so what would be the expected rate law from this reaction if step one is slow? Now remember, the rate law for the overall reaction is determined by the slowest step. So if the slowest step is step one, then the rate law for step one will be the rate law for the overall reaction. Okay, so what is the rate law for step one? That's going to be the rate equal to, and we'll call this K1 for the forward reaction. So that's going to be equal to K1 multiplied by NO, the concentration of NO. And since this is a 2 coefficient, then this is going to be raised to the second power, because the coefficient, the power is equal to the coefficient in the balanced equation. And so this is the rate law for step one. And since step one is the rate determining step, it's going to be the rate law for the overall reaction. And you'll notice here we have NO, which is in the overall reaction. So we don't need to do any substituting or removing of any intermediates. We don't have any intermediates here. So this is the rate law for the overall reaction. So we don't need that one there. We can just put K. And so that would be the rate law if the first step of the mechanism is the slow step. Okay, what about B? It says if the slow step, if step, oops, excuse me, if step one, or step two, I should say, if step two is the slow step and step one is rapid in both directions, meaning that it's at equilibrium, right? And it's fast. It's relatively fast at equilibrium. Again, what is the expected rate law for this reaction? And then it says, how should we properly represent the equation for the first step? So we're assuming that the first step is at rapid equilibrium. So the forward and reverse reactions are rapidly and they're at equilibrium. So the way to represent that is with a double arrow, right? So the first step would be at equilibrium, it's fast. And then the slow step would be the step two. So with that, how would we derive, or what would we expect the rate law to be? Again, the rate law is going of the whole reaction is going to be dependent upon the slowest step. Since step two is a slow step, we'll start with step two and write the rate law for step two. So in this case, the rate is going to be equal to, since this is step 2, we're going to call this K2. The reverse reaction we'll call K minus 1 for the first step. So rate is going to be equal to K2 times, and we have the concentration of N2O2 times the concentration of O2. Now notice here that we have an intermediate substance in our rate law. We can't have an intermediate substance in our rate law. We can have a product, we can have a reactant, but we can't have an intermediate substance, intermediate step. So here we have N2O2. So we'll have to get rid of that, and we can do that by using the fact that the first step is fast and at equilibrium. That means the forward and reverse reactions are equal to each other. The rates are equal. So we can represent that by the rate of the forward reaction, 1, is equal to the rate of the reverse reaction, which is -1. And if we write the rate law of those two reactions, so rate of the forward reaction of step 1 is equal to K1 times the concentration of its reactants. So that's going to be NO2 raised to the second power. So the concentration of NO raised to the second power. And then for the reverse reaction, it's going to be rate -1 is equal to K minus 1. And so the reactant for the first reactant, for the reverse reaction is N2O2. So here we have the concentration of N2O2. And since the rates are equal to each other, these are equal to each other, so therefore these must be equal to each other. So we could substitute these in for the rates. So that means that K1 times NO to the second power is equal to K minus 1 times N2O2. Since this is our reaction law, our rate law for the overall reaction, we want to get rid of this. So we're going to substitute in, we're going to solve this for N2O2 and then substitute for N2O2 in the equation. So if we do that, we can divide both sides by K minus 1, K minus 1. So that cancels out, and we get N2O2 is equal to this expression here. So we could substitute this in for this here. So this is going to be substituted in there. So let's go ahead and do that. So I'll go ahead and put this in. We'll get rid of this since we don't need this anymore. So that means the rate is going to be equal to K2 times K1 over K minus 1 times, and since instead of N2O2, we're going to substitute this in. So it's going to be NO concentration squared multiplied by the concentration of O2. Since we have K2 and K1 and K negative 1 here, we can just collapse that all together into K. So then the final rate law will be rate is equal to K times the concentration of NO squared times the concentration of O2. Let's go ahead and erase this. We don't need this anymore. And so this would be the rate law if, according to the mechanism for part B, if the second step is the slow step and the first step is a fast step at equilibrium. And so we get these two different rate laws. So this is the rate law if the first step is slow. This is the rate law if the second step is slow. Okay, what about part C? So part C asks us, what is the simplest experiment that could distinguish between the two different versions of the mechanism described in parts A and B? Well, let's look at the rate laws. So here, if the first step is the slow step, the rate of the reaction should only depend on the concentration of NO, nitrogen monoxide. But here, if the second step is the slow step, then the rate law is, or the rate of the reaction is going to depend on both NO and oxygen. So in this case, if the first step is the slow step, the oxygen shouldn't affect the rate of the reaction. If the second step is the slow step, then oxygen will affect. So the simplest experiment you could do is just look at how oxygen affects the rate of the reaction. So set up the experiment, use oxygen, see how the concentration or a change in the concentration of oxygen will affect the rate of the reaction. If you change the oxygen concentration and it has no effect on the rate of the reaction over time, then you know that this is the rate law. If oxygen does have an effect on the rate of the reaction, then this will be the rate law, and you know that this is the mechanism. You know that the second step is going to be the slow step. So that's the simplest experiment you could do. I hope this is helpful. If you enjoyed this video, if you liked the video, if I helped you in any way, if this was mind-blowing or maybe not so mind-blowing, either way, please like the video, share the video, hit that like button somewhere over here. Also, help me out. Subscribe to that channel, my channel, I mean. Hit that notification bell up there. When you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Have a great day and see you next time.